Hello everyone, welcome. My name is Srushti. I am the student of Sri Venkateshwara College of Engineering, Bangalore, from the Department of Computer Science and Engineering. The subject is Engineering Mathematics and the topic is about the Markov chain. Here the agenda: introduction to Markov chain, definition of a Markov chain, state space, transition probabilities, example, stationary distribution, applications, limitations, and the conclusion. Let's go with the introduction first. Introduction to Markov chain. Markov chain is a mathematical concept used to model random processes. It is named after a Russian mathematician, Andrei Markov. Markov chains are widely used in various fields, including physics, biology, economics, and the computer science. Definition and the properties. A Markov chain is a sequence of random variables where the next variable only depends on the current state. This property is known as the Markov property or the memoryless property. Markov chains can be described using a state space, transition probabilities, and an initial state. State expulsion. As the number of states in a Markov chain increases, the computational complexity also increases exponentially. Modeling assumption. Markov chains often simplifying assumptions which may not accurately captures the complexity of the real world systems. Parameter estimation. Accurately estimating the transition probabilities can be challenging, especially in systems with limited data. State properties. It is a set of all the possible states that the chain can be in. Each state represents a distinct condition of the system being modeled. The state space can be finite or countably infinite, and it also depends on the problem. Probabilities. It determines the likelihood of moving from one state to another in a Markov chain. These probabilities are requested by a transition matrix. The sum of probabilities for each state must be equal to 1. Markov chain with example. Let's consider a simple example. By taking a weather prediction, the state space can be sunny, cloudy, or a rainy. The transition probabilities can be estimated based on the historical weather data. For instance, if today is sunny, there is a 70% chance of being sunny tomorrow also, and a 20% chance of being rainy. These probabilities can be represented in a transition matrix. Stationary distribution. It is the probability distribution that remains unchanged after multiple iterations of a Markov chain. It represents the long term behavior of the chain. In some cases, a Markov chain may converge to a unique stationary distribution. Markov chains have numerous applications, including speech recognition, image processing, and text generation. They are widely used in natural languages processing to a model language patterns. They are also utilized in finance for modeling the stock prices and in genetics for studying the DNA sequences. Stationary distribution. A Markov chain may converge to a stationary distribution which represents the long term probabilities of being in each state. Irreducibility. A Markov chain is irreducible if there is a non zero probability of reaching any state from any other state. Markov chain. The property states that the probability of transitioning the next state only depends on the current state. Telecommunication network analysis, analyzing the call routing in a telephone network using the Markov chain model, estimating the call blocking probabilities and the system performances matrices, optimizing the network design and resource allocation, based on the Markov chain analysis results. Telecommunications Markov chains are used to model communication networks and to analyze their performances. Control systems. Markov chains helps in designing and optimizing the control systems for the various applications. Reliability analysis. Markov chains are used to assess the reliability of complex system and optimizing the maintenance strategies. Limitations of Markov chains. Markov chains assumes that future depends only on the current state, disregarding any past states. They are memoryless and they do not consider the entire history of the system. Markov chains are not suitable for modeling complex system with long-range dependencies. Markov chains are powerful mathematical tools for modeling the random processes. Despite their limitations, they provide a simple and intuitive way to analyze and predict the various phenomena. Understanding the Markov chains can be valuable insights in a wide range of fields. Thank you.